get rid of that water out of the bottom of the stack. They were able to open this hole up for us and provided a port for us that we could insert our probe and get our probe into the gas stream so that we could collect our sample. The second technical difficulty was power. Our pump and meter system requires quite a bit of electricity. We were concerned when we came that this line would not provide us enough electricity, but it really worked out well. We were able to get the electricity we needed to be able to collect the sample. So here's the pump and meter box system, like you're seeing up here, in use. You can see the sample probe here. This is the pump and meter box for controlling the flow through the probe. This is a silica gel system for removing water from the gas stream that we pull out, because we need a dry sample to be able to hit the pump and meter box. Here again, the silica gel system. Here's the probe, pump, meter box. This is cold as they would bring it up to the top of the kiln for firing. Another picture of the stack. Another picture of the top where they're firing the bricks. Again, electricity was always an issue, so here we are working on getting everything going. So this is the hole where we were actually able to take our sample with the zigzag furnace. This is the hole where they would let the water out. I would guess like this time of year, it was full of water. And we were able to get a positive stream. You can actually see the smoke coming out of the hole. You can see the white smoke coming out. So this is our probe inserted up into the stack. Again, another picture of the sampling location. So along with this, part of our objective was to acquire some ambient samples, and we were able to acquire some ambient measurements for black carbon at this site. These samples were taken upwind of the kiln to minimize any effects from this stack at this site. And so I'll be able to present that data in a few minutes. Again, this is another one of the mixers for mixing the brick making material. Looks like a big fan. It's connected to a diesel motor for operating the mixer. This is the brick making material, starting material. Here we are inserting or removing the probe from the stack. So again, one of the biggest difficulties we had was finding suitable sites for collecting samples. This is one of the sites we visited that we were hoping to be able to get into. Our probe was too long to be able to fit into the small space. This is actually the side of the kiln, and this is the stack here. And you can see the gases coming out of this hole at the bottom. This was a unique site from the other zigzag site in that they had two diesel motors and an electric motor. I know we showed up one day to the zigzag site and the power was out. It was on a load share system, and so we had to wait half an hour for it to start. And so a site like this, I thought really made a lot of sense because they, when the power was on, they could be operating the electric motor, possibly saving in diesel emissions and reduction in CO and CO2 coming out of the diesel motor. And the electric motor probably is much more efficient than the diesel motor and cheaper to operate. Here's what it looks like when bricks are being loaded into the kiln. As I said before, they'll start out with a layer of fired bricks on the bottom, put the raw bricks to be fired on top. off with another layer of fired brick on top. And then the final layer is where they would lay an inch or two of dirt on top to form the final seal. And then as bricks are moved, and then as the forks are being moved along, all these bricks would be fired in, down below. This is the second site we sampled. And again, going back towards technical problems and coming up with a suitable location to be able to insert our probe. These guys really came up with an ingenious idea. They've got some maybe 1 meter by 1 meter concrete sections that they can move or access to be able to get into the under sections of the kiln. And so we were able to pull back one of these pieces, one of these concrete pieces, and put a hole large enough that we can get our probe down in underneath the stack so that we could pull our sample from the flue gas just before it went up into the stack. And here are bricks being fired. You can see they leave some gaps in between the bricks. This would allow the hot gases to be able to circulate all the way around the bricks so that all the bricks are evenly fired. Here's another picture of the hole we were able to get into the stack with our probe. Here again, these guys are working to fire the bricks. Here, after the surface needs to be prepared, these ladies would remove the broken bricks and clean the area and seal the walls and get ready for new bricks to be fired. Here again are pictures of these long metal plates used to seal off sections so that you can control the amount of air, where the combustion air came from in the process, so that you could just fire the section that you want to fire. Again, this is a picture of our sampling probe. This is a PM10 and PM2.5 head. So we made the sampling equipment, we'll show you here in a few minutes, has a couple of pre-inlet pieces that are used to control what actual particulate matter is hitting the filter. And so we exclude everything above PM10 with this probe, or with this cyclone. There's a second cyclone here, so that anything below anything above 2.5 is collected here, and so that we know that everything being collected on the filter is below PM 2.5. And really, it should be noted that for most coal combustion sources, and I would say it's even true for this one, most of the time, we talk about PM 2.5, that's about 2.5 microns, that's smaller than human hair. That most of these particles that are coming out are more than likely in the 50 to 150 nanometer range. So that's 0.15 microns down to 0.05 microns. These are very, very small particles. And as other people have pointed out, the health effects from these kind of particles, these particles are actually small enough that when they hit the areoli inside your lungs, it actually can break that barrier and enter your bloodstream directly. It doesn't necessarily deposit in the lungs. It actually enters your bloodstream. They are so small. One more point, too, I want to point out on the size of these particles. Along with just the black carbon, I had mentioned metals are also with it. These metals are potentially, I'll start over again. These black carbon particles also have a very high surface area. If you were able to take one of these particles and make it just one atom thick, one of these particles, a very small this material could cover like a football field worth of area. And because of that high surface area, it actually will entrain a number of other pollutants with it. It actually acts like an absorber once it gets out. So if there's volatiles with it, if there are semi-volatiles with it, PAHs, dioxins, potentially these are captured by the black carbon, which again can enter the bloodstream directly. And these are really the primary cause of like cancers and other things from breathing these kind of particles. This is the coal from the second site. From from the traditional design. You can actually see here that compared to the very fine coal zigzag, this may actually contribute, these large pieces may actually contribute to the black carbon problem because of poor combustion. Here we are working on loading filters for the samples. These are what the ports look like when they're out of the kiln. It's just a short piece with a cap. Again, this is another view of our sample location of the zigzag. Here's another view of the inside of the fan. Another view of the bricks being loaded. So here are the filters. These are what the filters look like after they've been sampled. They start out beautiful bright white, and after they have loaded just a small amount of the gas from the kiln, they'll turn black or tan color. This is the transmissometer. This measures in two different frequencies. It measures in a UV frequency and an IR frequency. For the black carbon, we measured 880 nanometers, which is in the IR range. And the 880 nanometers is a region of the IR spectrum that is fairly free of other interferences. So really what we're looking at is, just like the sunlight hitting these particles, it's an IR effect where the black carbon is picking up the IR and holding onto the IR. It's actually absorbing the IR. And the 880 nanometer frequency of the IR, again, like I said, is fairly free of interferences. For IR, the two main interferences are CO2 and water. Neither CO2 or water absorb very effectively in this range. Which really allows this technique to look specifically at the black carbon particles. The other interesting piece is that it measures in UV. Like I said, this measures in two different frequencies. The UV tends to be indicative of organics. And so we have an entire other data set, possibly for organics, coming out of these kilns that have not been reduced. Rick and I have only been able to reduce the IR data at this point. So I think it could be very interesting to see what happens in the organic fractions. Again, these are filters with various loadings. Here's one with not as much loading, and here's one with a very high loading. And that's the end of the slides. And then I'd like to walk through the data that we collected. And then at the end, we'd like to possibly call a couple of Dr. Salam's students and help us set up the equipment. And we'll walk you through the equipment that we use to be able to collect these samples and generate the data that we're going to show. So I'm just going to talk just for a few minutes about the various pieces here. We've got the pump and meter box. This is a dry gas meter. This is very similar to like what you would use when you go fill up your car with compressed natural gas. They've got to have some way to be able to meter the gas going into your gas tank so you pay the right amount. This is the same kind of principle. So gas passes through the meter, and we can, just like on the gasoline pump or the gas pump, we can see how much gas we pulled through the filter. Again, as I pointed out, we've got a probe for being able to get a sample out of the stack. This probe is heated. We can heat this thing above the dew point of the water. Typically, we run around maybe 120 degrees C to reduce condensation. That also allows the probe to operate so that if there's water in the stack, or if you're in this kind of orientation that you don't have water running back down the probe into the filter, possibly ruining the filter, it makes sure that all the water stays in a vapor phase, and it can exit the train, exit into the silica gel train where we can drop out the water. so that when we generate data with the pump and meter box, we're actually generating a dry sample. Water actually can contain quite a bit of volume coming from co-combustion. Typically, for very good co-combustion, the gas stream coming out of a coal stack is around 6% moisture. So all the numbers I'm going to show today are dry numbers, which then could be corrected back to a wet number. We've got like I said, we've got the cyclone and filter holder. The cyclones are there so that we don't have any particles above PM 2.5 entering the cyclone. So that everything actually hitting the filter is respirable particles. These are actually very fine particles. We've got the filters. These are quartz filters. Unlike glass, the quartz filters don't melt till around, I think it's like 2,400 degrees C, versus glass, which would completely turn into a puddle at that kind of temperature. And then we've got calibration equipment we brought with us too to make sure that we're measuring the right temperatures and to make sure that the dry gas meter is operating correctly and that we're getting accurate numbers from the device. We're going to go through the equipment demo at the end, but I'd like to go ahead and just present the data and show you what we were able to obtain these last couple of weeks. So we had to make some assumptions, and we're going to provide these results in 3 different units. The first unit I'm going to provide is in concentration. What was the concentration of the gas that was exiting the stack? And we're going to provide that in a micrograms per cubic meter, in a grams per hour, in an energy unit, which will be micrograms per megajoule, and we'll also provide this in and I forgot which unit it is. It either be grams per, I think maybe grams per 1,000 bricks, so that we can actually see, if you've got 1,000 bricks, this is how much potential carbon was coming out of the stack. So to do that, we had to make some assumptions on how many bricks were being fired. So and how long it took to fire a section of bricks before they moved on. At the first site, what we found, or what we think we saw, were around 54,000 bricks per day. 54,821, just an estimate on the number of bricks we saw being fired. This turns into around 2,300 approximately bricks per hour coming out of this kiln. Next, we had to make some assumptions on the stack flow rates. Like I said, one of the technical difficulties was not having a hole on the side of the stack. We've actually got a device called a pitot tube. This is an S-type pitot. This is used for measuring stack velocities. This would be inserted into the stack, and we would measure the air velocity in the stack at various locations and be able to come up with a velocity in, say, feet per second or feet per minute for the gas traveling up the stack. Also, one of the difficulties with not having a port is that we don't actually know precisely the diameter of the stack at that location. And so we made some measurements at the bottom, and we made some assumptions on what possibly the diameter was at the top. And so we came up with a stack diameter at the top. We came up with a velocity, and we came up with an actual stack flow rate. And so we estimated the stack flow rate at our first site, this is at the zigzag location, of around 1,200 cubic meters per minute of gas traveling up the stack. We also made some measurements of this fan. And so the fan has a volume, internal volume here, about 2.9 cubic meters. We know the fan was operating at approximately 1,100 RPM. Because of the design of the fan and possibly other losses in the system, just through pressures and just because of this actual fan design, we put the fan efficiency at around 50%. And so we've calculated from the fan data that we were at around 1,600 cubic meters per minute. Very similar, very close to what we've calculated just visually observing the stack at around 1,200 cubic meters per minute. For my calculations, we went with a lower number. We used this 1,200 cubic meters per minute. Again, the Site 2 was a slightly larger facility. They could fire a few more bricks, or at least we observed it looked like they were being able to fire more bricks per day. The actual width of the interior of the furnace was around 3 foot longer than the first site. The first site had an internal distance between the walls of 27 feet. This site had an internal distance of 30 feet. And so we were computing, very close, but we were computing the second site, we were getting around 3,000 bricks per hour being fired. So here's our first set of results from Site 1. And here, like I said, we've got a black carbon concentration, and I've listed this in micrograms per dry standard cubic meter. And we were able to collect these filters here, 4 through some different numbers. We pulled different filters out of the box, but these are the samples that we were able to collect from the first site. And by multiplying these concentrations by the stack flow rate, you actually get a BC emission rate of somewhere between 6.4 kilograms per hour at a high number, all the way down to 33 grams per hour of black carbon being emitted just from this one stack. And after the first few runs, we noticed that if we observe just the emissions coming out of these stacks, sometimes it was very white, sometimes it was very dark. Gene actually has been to a special school that we call smoke school, and it's actually used by the U.S. Environmental Protection Agency and by state and local agencies in the United States for just estimating emissions coming out of a stack. Obviously, you don't want to see very high opacity, and that's where we get this number, is opacity. That's kind of the direct gauge of how dark that cloud was coming out of the stack. At 100% opacity, that's black as those cases right there. That's no light getting through, versus 0% opacity, which is like this room. You can see right through it. Versus, say, like cigarette smoke, maybe like 10 or 15% opacity. So these are the kind of opacity numbers that we're measuring. Just visually, this is just a visual. You have to be at the right angle with the sun, you have to be at the right angle with the stack, and you observe as the smoke comes out, the steam will dissipate, and then you will be left with opacity. You're left with what's left. And it can be a nice gauge for the amount of particulate being emitted from the source. And so you can see here that, at 5-10% opacity, we have some fairly low numbers. We missed a few in there. We weren't able to collect one on every run, opacity number. But you can see here, like when things jumped higher, when we're in the 20 to 25% opacity range, you can see the numbers come up. Again, here at the bottom, you can see like we're at almost 5,000 grams per hour. The opacity was around 20%. Again, here 2,000, we're in the 20 to 25% range. We missed it on the 6,400 number, but I can probably guarantee you it was fair darker than it would have been at one of these 5 to 2% opacities. So we wanted to, EPA also has a method called Method 19, where if you don't know the exact energy content of the fuel, that you can assume some energy content of the fuel. And we can go through these, if people are interested, we can go through these emission calculations later. These were all covered in our quality assurance project plan. But these are emissions versus energy units. And these are really the same data. So, this is and this is actually corrected for the CO2 content in the stack, so that we know that, if you burn this much coal and it's got this energy unit, you've emitted this many micrograms of material out of the stack. We also wanted to provide you some emissions data first based on the number of bricks being produced. And these are directly related to the grams per hour and those brick numbers that I showed you at the beginning, based on how many bricks per day we think we were getting out. So these are actually grams of black carbon per 1,000 bricks. And this just shows you the range of black carbon we saw. This is in the zigzag site, this is site 1. And so, anywhere from 2.8 kilograms down to 14 grams of BC black carbon per 1,000 bricks being fired. These are the results for stack 2, the site 2. Again, similar flow rates. Because it doesn't have a fan, it was naturally drafting. But because it was a larger stack, this stack was around 20% actually larger in area, so it allows more gas to be able to travel up the stack. But because it was naturally drafting, we got almost the same number. So this stack was operating around 1,700 cubic meters per minute. These are the same results like we saw from Site 1. I provided these in a micrograms per dry standard cubic meter. And these emissions at the traditional site were much higher. We had some low numbers, when we had some decent opacity of around 32%,